So we had a mass that was moving with some initial speed v naught sliding, and there was no friction. And over here, we had a spring that was going to get compressed. And I want to make it really clear what the coordinate x that I'm going to use means. I'm going to measure the position of this front end of the spring using the coordinate x. Okay? And then I want to consider only the time of the motion when the mass is in contact with the spring. Okay? So at time t equals 0, it just touches, and the energy in the system is just kinetic, 1/2 mv squared. Okay, so the initial energy would be 1/2 mv naught squared. And the interesting thing comes about if we say, well, look, if you do this and it compresses the spring and then reverses and comes back, one can observe that the speed is exactly the same v naught going to the left after the mass leaves contact with the spring. And so it must be that the energy in the form of kinetic energy of the mass is converted into potential energy in the spring, and then that reverses and is given back to kinetic energy. And that's what we use to figure out the constant 1/2 in the expression for the spring energy. So if I'm considering the phase of the motion during which the mass is in contact with the spring, then is it fair to say that this should be the speed, x dot should be the speed of the mass? Is x dot the same thing as v of t, where v of t would mean the speed of that mass during this phase of the motion? Is that clear? So if it's moving, if the mass is moving to the right, the time rate of change of its point of contact with the front end of the spring would be its velocity. Okay? So we'd have this expression, and then what we determined last time, whoops, let's not do that, is this is the correct form, because if we take the time derivative of the energy, so help me out, what is the time derivative of that term? Okay, so mx, okay, so whose rule do I have to use? Madam Chain and Mr. Product. So this is a function squared, so I'm going to get twice the function times the derivative of the function with respect to whatever it is I'm differentiating with respect to, and that's circular. So we would have x dot, and then times the derivative of x dot with respect to t. Okay, and on the second one, and notice that the 2 that came down wiped out the half. Same story here, the 2 that comes down is going to wipe out the half there, and I have k x, that's from the product, or the power law, if you like, and then I have the derivative of that function with respect to t. Okay, and I want to be able to show that this thing is really 0. So it looks to me like I have a common factor of x dot, so let me factor that out. And I have ma, or mx double dot, plus kx. And allegedly, that's supposed to be 0. So let me do my isolation diagram over here and put on the forces. So I'll have gravity going down, and I have a normal force coming up, and then I have the force of the spring on that face of the block, and the force of the spring that way will be kx. Okay, having defined x as positive to the right, that's the direction that's positive for my acceleration. And so from this isolation diagram, I would get ma is equal to minus kx. So I can replace this with minus kx, and so it works. That is, with this form of expression, which we got out of dimensional analysis up to the factor of a half, then it is true that the time derivative of the energy is 0. Okay?